Okay, so let me start by answering probably a question that was posed yesterday at the end of the lecture about the integration of current algebroids. Properly means to give the proper references rather than giving a complete answer. So there is this very special paper called some title containing the words homotopy and symplectic. Simply gradient this one by Pablo Echeverra. And here you can see actually there is a table at the very end where he draws a very nice parallelism between like symplectic Poisson and then current algebroids. So you could say like this integration corresponds to this symplectic two groupoids, whatever they are. Okay, there is a paper a couple of years later that actually checks formally that that's the case for exact current algebroids. And exact current algebroids, they are actually like this Tm plus T star M that I put yesterday. The only thing you are changing the bracket. The bracket I put is not the only bracket you can have on Tm plus T star M that makes it a current algebroid. Those integrate to symplectic two groupoids. I said it's not completely set in the sense that, okay, there are other approaches. For instance, this recent paper just 3 years ago, and it talks about Diracoids, whatever that is. Okay, having said this, let me then continue with what I was doing yesterday, and I left a question open about some maximally isotropic subspaces of this V plus V dual. Okay, so let me actually remember why we were doing this. At the end of yesterday, what we had was this object, which was Tm plus T star M, and then we saw it had a natural pairing. It had a bracket, which I defined, as I said, now you can define others, and they had a projection to Tm, and this is a current, what's called a current algebroid, because it satisfies very nice properties. For the bracket to be skew symmetric is not one of them, but the other ones are pretty nice. So we gave a definition, which was a Dirac structure is a subbundle of maximal isotropic. Let me just do it in a short way. Maximally isotropic and involutive subbundle L inside Tm plus T star. And why did we define this? Okay, because we saw that actually the graphs of presymplectic and Poisson structures, they fall within this more general framework. So here we have a larger class of structures. And the first question is to know, okay, at a point, how do these structures look like? Okay, so this is the question I posed yesterday, which was like for V plus V dual, okay, a vector space, describe maximally isotropic subspaces. Okay, and here I can forget about involutivity, which is actually the geometric part, but also the hardest. And I suggested how to start it. I said, okay, this is the question, this is the answer. Consider, okay, these are the spaces, I'm going to call them L, okay. And I consider E, which is the projection to V of this L. And what I said is I'm going to do it kind of as a graph, okay? So I want to answer the question, oops, sorry. Put this in tablet mode if I can. No, okay, I cannot. So for X in E, what are these possible? What are alpha in V dual such that x plus alpha belongs to L. Okay, so this is the question now. So first thing, it's to realize that actually if I have x plus alpha and I have x plus alpha plus something else belonging to L, okay, I have two different ones, and the difference between the two of them is some gamma, which is some element in the V dual. So then what will happen is that their difference, okay, which is gamma, is going to be an element of L, but it's also going to be an element of V dual, okay? And actually, this is an equivalence, okay? Because I can also, if I have an element in L intersection V dual, since it's in L, I can just subtract it from here, and I have that those two things are in, is say like this. Given x plus alpha in L, then that one is in L, if and only if gamma is in L intersection V dual. So now the question is, what is L intersection V dual? So first of all, if I get an element here, say of beta in L intersection V dual, since you know how the bracket is, okay, since you know that now if I take x alpha in L and I take this beta, this has to be 0, and you know what this is because this is beta, 1/2 of beta of x. So actually it will be nicer to just put the 0 here and to put here 1/2 of beta x. So you know actually that this beta is going to be in the annihilator of E, okay? Because here I can put any element x plus alpha in L, and E is precisely the projection of the elements of L to V, okay? But on the other hand, if I take now the annihilator of E and I consider this space, L plus annihilator of E, for the same reason, this is an isotropic space, okay? Is isotropic. And since L is maximally isotropic, that means that actually they must be the same, okay? Otherwise, L plus annihilator of E would be bigger. So it says actually that the annihilator of E is inside of L, and I know also that the annihilator of E is in V dual. So I have this intersection here. So from that I deduce that I actually have an equality. L intersection V dual is the annihilator of E, okay? So now what can I do now? So I can describe a map, okay? The map I was going to define before, I have a map which is for each x, you can map all the elements that, all the alphas that can be, that will give you this thing here, x plus alpha in L. And what I just proved is that this thing is just a co-class, alpha plus annihilator of E. So this is my map. Okay, for every vector, this alpha is like, say, an initial alpha, and then I know that what I get is a coset in this quotient space by annihilator of E. What kind of map is this? This is a map going from V to what? So to V dual quotient by annihilator of E. Okay. And the thing is that this is something I know because this is precisely, sorry, not from B, from E. This is, it has to be from E, okay, because X belongs to E. And what I do is I map X to here alpha plus annihilator of E, okay, whatever alpha is, some alpha such that X plus alpha is in L, that I won't be able to describe concretely now. And this is isomorphic to E dual. And actually the isomorphism is just going to alpha, which is in V dual, restricted to E. Okay? So given a maximally isotropic subspace, I'm able to define this map. Okay? This map I'm going to call it epsilon, going from E to E dual. Okay? Now, the thing is, I also know that my space L is maximally isotropic, so I know some property about this map epsilon. So since I know that x plus alpha with itself is 0, and this I know is alpha x. Now the thing about the alpha is that alpha, when restricted to E, is precisely epsilon of x. So this is actually epsilon of x, x. Okay, or if you want, you can see epsilon as a two form, as something that takes eats two elements from E and gives you a number. So this is epsilon x, x. So this is telling you that actually this map is skew symmetric. Okay, it belongs here. Okay, we started as projects, and now how do I describe all the possible alphas? So they will be, okay, those they will be given by this element epsilon, which is skew. So let me just sum up this now nicely after I put some raw math on the board. So the proposition now is, okay, what happens if I go the other way? Because now I see for any L, you can produce the projection and this Q map on the projection, okay? So now what I want to say is that actually, if you give me such a subspace and you give me such as Q map, you can define something which is some L associated to E and to epsilon, which will be just, well, you can imagine the x plus alpha such that x has to be in E. And alpha has to be like kind of epsilon of x. So the way I write this is just to say that alpha restricted to E equals epsilon of x. Okay? So it turns out that this space for any E and any epsilon is maximally isotropic. And also, what's more interesting is that actually all maximally isotropic subspaces are of this form. Okay, so we have now a complete answer to this question. Okay, I already put the details, like the important details, because it shows you how it's working. There are some other small details to fill in, which I won't do now, because I think it's much better just to see examples. So, okay, what are examples of this LE epsilon that will give me a maximally isotropic subspace? Remember that we had actually some maximally isotropic subspaces. We had Tm. So how is Tm one of this kind? So Tm is just L of, now I'm going to do like the global version, okay? Instead of using V, I'm going to put Tm to come back slowly to geometry, okay? So LTM0 equals Tm. Okay, so at each point, if I put here an x, so you have here an x, but since that works globally, so I can also talk about this in here. Okay, so yeah, when this is 0, okay, so E is the total, so the one form has to be 0. Okay, I have no option because the epsilon is 0 and the E is the total domain. Okay, So I only have Tm. T star m, look at T star m is actually the L of the zero space and the zero map. Okay? Why? The zero space because I don't want to have any, this for T star m. The zero space because I don't want to have any projection, and the zero map because on the zero space I only have the zero map. So I don't have any other option. Okay? So these are the two we had. There are actually more. We also had this one, that L Tm omega. Okay? So this, again, if you think about it for omega wedge to, okay, omega to form, this is actually the graph of omega. Okay, because here again the E is the total, so this is just alpha will be omega x. Okay, so that's it. I only have one option, and it's the graph of omega. And another example would be to take, and this to do it globally, I have to say, okay, E, I have to take as a bundle. I can consider L E 0. Okay, so these ones are going to have projection to E, and since the map, this map here epsilon is 0, what's telling me is that the alpha restricted to E has to be 0. But if the alpha restricted to E has to be 0, that means that I have the annihilator of E. So this is again a direct sum, okay, annihilator of E. So this is another example of how maximal isotropic is given by these two ingredients, the projection and this map. Okay, so now let me tell you why this is useful for the study of Dirac structures. Okay, so what I did here is I played before the linear algebraic game. I went to a vector, to a point, and I was with this vector space. Then I've done now something geometric. But the fact is that this E doesn't need to be of constant rank, and this is one of the interesting things. Okay, so let me just say first, observe first that a Dirac structure, okay, will determine at each point, okay, determines at each point of my manifold is determining this EP, this space, and also this thing here. Okay, this. Okay. Now we have to be careful, but that's the main interest of all this course is that actually the dimension of EP is not necessarily constant. Okay. So, but the good thing, okay, is that this E, despite not being necessarily constant, is going to be always, okay, is tangent to what's called a foliation. Okay, what is a foliation? A foliation is a nice partition of your manifold on submanifolds. Okay, so I'm skipping here the technicalities with words like nice. So I will say a few words of your manifold into some manifolds. So this n is now the union of some n alphas. Okay. Now the thing is, this partition, because I said that the dimension of EP is not necessarily constant, and this C not it's always tangent. Actually, I should say it's always the tangent space to a foliation, okay, to one of these leaves. So this means that if I have say this is my manifold, so what is a foliation? So it would be saying like decomposing this manifold here into some manifolds here. Okay, so all this, if you want the most trivial example would be just take the plane and take horizontal lengths. Okay, that's a foliation of the plane by some manifolds. It's a partition of the plane of manifolds, and actually the regular foliations look like this, but they don't need to be regular. If you take a partition of the plane by circles, you have to put a point in the middle, okay? So, and that point is not of the same dimension. The thing I'm now describing is that this E, remember, E is inside the tangent space to your manifold. What I'm saying is that actually there is a foliation such that your E is always in those directions. So the E is always going in the direction of the leaves. Okay, this is something you have to prove, of course, is not. Okay, and here your E has to be always in the direction of your leaves. Okay, of course, if the leaf is a point, so okay, there won't be anything there. Okay, and not only this E is somehow describing this foliation, integrates to this foliation. It's also that this epsilon, okay, is closed along any leaf. Okay, so say D of this epsilon, when you restrict it to an alpha, this is going to be 0. Okay, here I'm going to say something which is important to understand it, is that, let me stress it, EP is the tangent at P of an alpha for P in an alpha. Okay, this is the key, that there is such foliation, M divides, and your EPs are the tangent spaces of this. So what this is doing is actually a Dirac structure, because of these two ingredients that we described linearly, the projection E and this epsilon, which is like a two form. The projection E is cutting your manifold in slices, okay? In such a way that actually the tangent space to each slice is E. And it turns out that this epsilon, when you look at it on a slice, it turns out to be a closed two form on this slice, okay? Because remember, this epsilon is actually a closed two a two form here, okay? So since I know if it's at a point, this is the same as wedge of T star P and alpha, okay? So this is presymplectic. So what can be proved, I'm just giving the idea, not the formal proof, of course, and this is a theorem that was the first things to be proved for Dirac structure. So what a Dirac structure is a presymplectic foliation, determines, okay, a presymplectic foliation where the leaves, I insist, they don't need to be of the same dimension. Presymplectic foliation, okay? So this is a lot of geometry, okay? All of a sudden, because we consider these L's that were maximal isotropic and involutive, we have come up with this new structure that has a very concrete geometric meaning. Let me put it into context, and this is something that Enrique Burstein explained to me once, this very nice diamond. Like, if you think about a symplectic manifold, say your phase space, okay, you know that sometimes you have to move along constraints of your mechanical system, okay? So in these are constraints as a manifold, okay? So as a manifold, your omega stops being symplectic because it may be degenerate. To start with, n may have odd dimensions, and there is no way to have something symplectic on odd dimensions. But still, it will be a closed two form. And actually, we define closed two forms to be these presymplectic structures. So this is omega n. Okay. So this omega degenerates somehow. Okay. To presymplectic. So, but the thing is, omega, it also determines, this is something I didn't say before, but any symplectic structure is presymplectic and also Poisson, because you can just take say the inverse of this thing, like kind of omega minus 1. You can see it as a Poisson structure as well. And in a mechanical system, when you have symmetries, what's happening is that actually you are touching this side of the story. So if you want, let me put it like this: when you have symmetries on your mechanical system, everything will be described as something which is Poisson. Okay, a Poisson structure. And the thing is, a Poisson structure, it's something which gives you a foliation by symplectic leaves. Okay, so it also has this geometric meaning. Now, what Courant was asking when he found Dirac structure was a question of okay, you know what happens to a mechanical system when you take constraints, you go presymplectic, or when you have symmetries, you go Poisson. But why don't you have both of them? Because maybe you have both. What happens then? What kind of structure do you have? And the answer is Dirac structures. Okay, so here Dirac lies as the common definition that will allow me to talk about systems that have both constraints and symmetries. Okay, and look, Dirac, I have just said that it is a foliation by presymplectic leaves, and everything makes sense because actually a presymplectic manifold, is just one leaf, one presymplectic leaves. Okay, so this presymplectic is contained in Dirac, as we know, and Poisson is also contained in Dirac in this geometric way because symplectic leaves are in particular presymplectic, so they also fit nicely, okay, into this picture. So Dirac, okay, in this sense, so it's closed under taking some manifolds and taking symmetries, okay, with these two operations that led us to presymplectic and Poisson. If we repeat them, we get to Dirac, and Dirac is the nice category for that. Okay? And this is what I wanted to tell for now about real Dirac structures. So let us now go complex, and let's go now to the other side of the story I told, because you remember there were two sides: Dirac structures on one side, and then there were generalized complex structures. So let's come up here, and now we start with generalized complex structures. Okay, so let's first recall the definition. So remember, I was putting this definition in terms of the operator J. So I said a generalized complex structure is a smooth bundle map. Okay, here I insist. Okay, as I said yesterday, it's just a section of the endomorphism bundle, but let's just say here J is an endomorphism of Tm plus T star m, and now it satisfies several conditions such that, to start with, okay, it's a complex, let me put it kind of curly, it's complex, so J squared is minus identity. Okay, I said it is Q-symmetric, which I wrote like this, and plus an integrability condition. Okay, what I wrote so far, it would be a generalized almost complex structure, and then now I have the integrability condition, which is like the plus I eigenbundle. Now the plus I eigenbundle is some L living inside the complexification of this big thing, okay? Has to be involutive with respect to the bracket we have there, which is the Dorfman bracket, okay? And this is involutive. Okay, so what am I going to do with these structures now? So with this structure, what I'm going to make use is of this triple way I have of understanding complex structures, okay? So on a vector space, okay? So recall something first. If I have just an operator, this is straight J, which is an endomorphism squaring to minus identity, okay? I have a way of, by considering its plus I eigenspace, of getting L inside L inside VC such that L is just transversal, like a zero intersection with its conjugate. And I can go the other way as well. I can go the other way because I can always define some J, which is I when I restrict it to L is just multiplication by I, and when I restrict it to L bar is minus I, okay? This is well defined, and actually it defines something on the whole of VC, and because of this property of being conjugate when I conjugate on the domain, so it actually gives me a real endomorphism, okay, of my vector space. So I have this correspondence, okay? So I can make use of this because now at every point I do have an endomorphism such that J squared is minus identity. So now I can just say, well, a generalized complex structure induces, and actually I just put it in the definition, I need it in the definition in order to talk about integrability, okay? But induces such a thing and such that, now what I want to do is to say the properties it has. It has this property, okay? Why? Because it has it linearly here, okay? I just replace my vector space V by this Tn plus T star m at every point. And, okay, I still have L is involutive. Now, the issue is that generalized complex structures, they satisfy an extra condition, which is this one here, okay? So how do we express in terms of L, okay, how to express J plus J, that this is 0, okay? So now the idea is J plus J dual equals 0 is a metric condition. It's something that is expressed in terms of the pairing. So whatever I say about L, it will also have to be expressed in terms of the pairing, okay? Since this is a metric condition, when I say metric, I refer for the pairing, then I have to use the pairing, okay? So actually, what one can see is that this L, this generalized version of the plus I eigenspace, is maximally isotropic. So, and this is so easy that I'm going to do it formally, okay? Because remember, we know that, okay, for V in L, JV is IV, okay? This is a definition. But also we know that J is skew symmetric as well. So since we know that J is skew symmetric, so I will also know that 0, okay, this, okay, let me put it in the way I put it yesterday. What does it mean to be skew symmetric? Means this, okay, J U V plus U J V equals 0. As I said before, with all these metric conditions, as long as the characteristic is not 2, actually, you are better off just considering what happens when they are the same, okay? Because it will be much simpler. So what I can say in this case is, because it's symmetric, is that JV pairing with V is 0, okay, because it's skew-symmetric. So this is what skew-symmetry means in the simplest way. But I know what JV is. JV is IV, and this is linear, okay? So I have that VV equals 0 for all V in L, and I proved yesterday that actually, because of this thing of characteristic not being equal to 2, this tells me it's isotropic, okay? Isotropic, but I said more, I said it is maximally isotropic. But the thing is, because L is the plus I eigenbundle of this J squared plus identity, and I only have 2 eigenbundles, I and minus I, and because the endomorphism is real, okay, every time I have a vector of eigenbundle I, its conjugate will be an eigenvector of eigenvalue minus I. What I'm saying is that actually they are both the same dimension, which is in this case the dimension of complex dimension of L is the dimension of your manifold, okay, which is the dimension of Tn. So, and this was exactly the dimension of the maximally isotropic subspaces. Okay, so once I see that it's isotropic, I check it has the right dimension. So I have that it is maximally isotropic. Okay, so that condition, I know it at least, okay, it's telling me that it's maximally isotropic, and look what's happening now. I'm saying now that a generalized complex structure induces L with some condition, but L is involutive and maximally isotropic. Okay, look, this is actually this L, this maximally isotropic plus involutive is my definition of Dirac structure. Okay, so this has a name. In this case, because I'm considering complex, this will be complex Dirac, okay? A structure. So it's a complex Dirac structure. It is not any, because actually I have an extra condition, which is this condition about L intersecting L bar in 0, okay? So in the, as a proposition now, I can say that there is a correspondence, okay? This, again, I just showed part of the math. There are some details to fill in, but there is this correspondence that extends the linear algebraic one between J, a generalized complex structure, and L, complex Dirac, such that L and L bar is trivial, okay? It is a very important fact, which I won't prove, even though it has a linear algebraic proof as well, and it's not difficult, but that these structures, actually these generalized complex structures, if they exist, if either this J exists or this L exists, it has to be in even dimensions, okay? So let me just put this fact at this point. If M admits generalized complex structure, what happens actually is the whole story is if M admits a generalized complex structure, what it also admits is an almost complex structure, okay? So, and we know that in order to admit an almost complex structure, the dimension of M has to be even, okay? So this is a basic fact that you can prove in a linear algebraic way. And the other fact, this is geometrical, and actually it will be also important for us. Okay, now we've been talking for more than 10 minutes, I think, without putting an example. So it's time to see some examples. Okay, so we had two examples of generalized complex structures. When I motivated the introduction of generalized complex structures, actually, when I wanted to consider those endomorphisms, it was because I could fit two classical structures in such a way. And those classical structures were a complex structure, and I defined this map minus J 0, 0, J dual, okay? And for this one, what I can see is what is the plus I eigenbundle for this? Well, it's easy kind of because this is minus J. So, okay, the plus I eigenbundle for minus J is the minus I eigenbundle for plus J. So this LJ, I'm going to call it, is going to be just the 0, 1 vectors for that complex structure. Okay, if you remember your linear algebra for complex structures, and then I will have, okay, so now for G dual, which is it is what it is. So, okay, the plus I is actually just by definition the 1, 0. The 1, 0 forms are defined as the plus I elements for this structure. So this is actually boring. But we had another example that was more interesting. We had a symplectic structure, okay, which was given an endomorphism just by considering omega as a map from Tn to T star n and minus omega inverse here, okay? So what is L omega? What is now the plus I eigenspace of this thing here, okay? So, well, one can actually think a bit about it, saying, okay, like if I want this x plus alpha, I want it to be I times x plus alpha, okay? So, but now this, you know what it is, because this is just minus omega minus 1 of alpha plus omega x, okay? Well, so from here, yes, you just need to look at one of the sides. So let's look at the simple one. The one form, omega x, has to be E alpha, okay? So that means that alpha is minus I omega x. And the other one follows. So actually, these things here are x minus I times omega x, such that with x being any element in here. Okay, so if you want, is the graph, actually the graph of minus I omega. So this is my generalized complex structure seen as a bundle, as a complex Dirac structure, satisfying. And now you can see actually, if you want, you could take all the properties of the complex Dirac structure seen as a bundle, maximally isotropic, involutive, and L intersection L bar equals 0, and check that actually both of them satisfy those properties, and they satisfy them in a very transparent way. And by this I mean that if you take omega, which is not closed, okay, so okay, you'll be missing the integrability condition, okay? So everything, like every property corresponds, there is a clear thread that takes you to the original property. Okay, so that's nice, but I want to go one step further, because we know that complex structures, I can see them that way, and there is a bit of a funny way, another funny way to see complex structures. Okay, so given one of these L's, okay, such that L, no, given the J, so you can take, by considering 0-1 forms, okay, and here I'm going to put this is between quotes, okay, just to take a base of the 0-1 forms, and you take the M01, so you end up having some differential form, okay, some here I mean it's not differential in this case, some M form, okay, actually some decomposable, because it's just a product of, but okay, here is a composable, but actually, yeah, here it gives me, okay, let's say it gives me some M form. In such a way that, and there was a process to go back, which is if you give me that M form, okay, some, if I take the annihilator of that form, and by the annihilator, what I mean is the elements in my vector space such that when I insert them in the form, okay, say, actually I'm going to use this geometrical notation, that's going to be 0, okay? So here, remember, what I'm thinking just is to say this phi is 0 form, and of course, the annihilator of a 0 form, okay, there are the n0 vectors. Annihilator of 0m are m0 vectors, okay, and the m0 vectors are the 1, 0 vectors. The 1, 0 vectors, and the 1, 0 vectors are precisely the plus I eigenspace. Okay, this is what's going behind the scene. Okay, so this, it works when we know what it is about. Okay, bear in mind, here I said sum. So this sum, it's very like, okay, I don't know how to start from that side, to be honest. I know how to start from here. I start from L, I go to the 0 form, and I know how to recover my original L as an annihilator. Okay, let's see what can we do in this generalized geometric setting, because actually this approach will be the one that will help us more. So let's see if we will get any close to this, okay? And what we need is, I want for some form to define a subspace, okay? So before I was making use, okay, of this operation, okay? So that thing is for vectors, not for vectors, okay? I'm going to say, we would like, I'm going to express here my target, would like to have some analog in such a way that you give me some differential form, okay, arbitrary, and I can give you some annihilator of some sort, but now inside Tm plus T star M C, okay? Here, by the way, I should put the C, and here I should put also the complex. I think, yeah, those are all. Okay, so how do I get this? Well, first we need an action. We need an analog of this operation that for every of these I operation, okay, the insertion operation, what it does is you give me a vector over one point, you give me a form, and I can give you another one. Actually, I can put a -1 if you want here, okay, which is give me x, give me t. So just do this in here, okay. This is what we've called ix, okay, by definition. Okay, so what's an analog of this in our situation? So the analog would be, so kind of this analog, it has to be some kind of action of, okay, of these guys here, of Tm plus T star M complexified on, and here, yeah, just at the beginning when one goes complex, it's always missing the complex to start with, but we'll, actually here I don't need the, yes, I need this, okay. All this complex on the complex forms, Okay. Here I'm using the bundle instead of the sections. Okay, because it's a linear algebraic operation. So let's just face our issue. We need to define an action. Instead of doing ix phi, I need to do some kind of ix, but now ix plus alpha on phi. Okay, I'm going to denote it like this. And I want to get another form, another element in here. Well, I know already how to do it with a vector. So I may as well just take here ix. Okay, I'm defining this action. And now what can I do if I have a one form and you give me a form of any degree and you want a form of any degree? Well, so the operation we have, I mean, like we don't have many. Is this one here? Okay. So this is an action. Is this helpful? We don't know, but we have to be careful because look at something, okay? Before, if I do ix of the same phi, since these are skew, this is, okay, in particular they alternate, so this is 0. Okay, this was an important property of the insertion operator, which I didn't say, but it's not always too late to remember. Is the same happening here? Okay, we'll have to check. I mean, like these are some of the things that we can do. Does it happen here as well? Okay, so what I have to do is to act twice. So I have to do x plus alpha, acting on what? On x plus alpha, acting on this Greek phi. So I have x plus alpha, acting on what? On ix phi plus alpha wedge phi. Okay, now it comes the non-trivial x. It acts as the insertion here. Okay, that's 0. Good. You start well, okay. And now ix of this whole thing. So, well, this thing is going to be a derivation. Okay, I will do it later. And now I have plus alpha, which ix phi. And look, here I'm lucky because alpha, which alpha is 0. Okay, I can put it here. Is 0. Okay, and there was this other term which was ix phi, which is also 0. Okay, okay, let me develop this. This acts as a derivation. So I have ix alpha times, because it's just a function, phi plus, now plus no, minus, because it's a one form, okay? So that's actually important, minus minus alpha, wedge ix phi, plus alpha, wedge ix phi, this goes, oops. So I get ix alpha phi. Well, but this happened before to us. When we were doing the bracket of two generalized vector fields, it wasn't skew. Why? Because I got d of ix alpha, which was d of the pairing. So I'm getting the same here. X alpha pairing times p. Okay? So does it happen here as well? So, well, the answer is no, it doesn't happen here as well. But actually, it's even better. Okay? This condition. Why? So we'll see it in a second. Okay. Let's first do the analog of the spaces I want to define, which are annihilators. So now I want to define one of these Dirac structures as an annihilator of a form. Okay, and I would say, okay, the annihilator I can consider here are the x plus alphas inside Tm plus T star M complexified, such that when they act on this form, this gives me 0. Okay? Note something already here, that for a function, if you give me f, which is non-vanishing function on your manifold, actually the annihilator of this phi and the annihilator of f times phi is going to be the same, okay? Because this action is linear by linearity, okay? So that's nice, a nice property to have, and this is the way I would like to describe some of my L's, okay? I'm very far, I'm still very far, okay? I just started to know what is the analog of this insertion operator, okay? So examples, let's see what's happening here with this annihilator. Is it true that I can write some of the examples I have with this formalism? Okay, so let's take some forms and let's look at their annihilator and see what they describe. Okay, so here I will start with some very simple differential form, because we have just arbitrary degree. I can just take the function which is equal to 1. Okay, this is an element as a section. I can see it as a section, a 0 section complexified, of course, of my manifold, and this is inside all like the whole forms. Okay, now what is an annihilator of 1? So the annihilator of 1 are the x plus alpha acting on 1 such that this is 0. Okay, now x is a vector field. If a vector field is acting on a constant function, is derivating a constant function, is 0. Okay, giving me 0. There's nothing else there. Whereas alpha does alpha wedge. So alpha wedge 1 is alpha. So actually, none of the 1 forms will annihilate my t star m, sorry, my 1, but all the tm is annihilating this thing. Okay, so actually I'm recovering. Okay, this is not TCM. This is not a generalized complex structure, but we've seen it before. Why? Because it's maximally isotropic, at least. Okay, now more examples. So I may have to put some hypotheses in order to write examples globally. This is something that will always work locally, but here just let me say, okay, if the manifold is orientable and you take a volume form, this a volume form means a top differential form. Here, okay, this is a bit of the opposite example. Okay, if I give you a volume form, no vector field will kill the volume form, whereas every form, because the volume form is a top form, every form will kill it. So this is actually TCM. Okay, so this is the way I recovered like the simplest maximal isotropic subspaces. So more examples. I talked before actually about taking a subbundle, okay? And let's assume as well that for this subbundle I have also like a volume form of this subbundle. Okay, let's assume exists phi, which is, well, not of this subbundle, sorry, of the annihilator of this subbundle, of annihilator of phi. Okay, so by this what I mean is you take a basis of the annihilator of phi and you do like the annihilator of E and you do this thing. Okay, so this is a basis of annihilator of phi. This, as I said, works always well locally. Globally, you have to assume some hypothesis, but okay, let's play along. So first non-trivial example, what is the annihilator of the volume form of annihilator of phi? Okay, so, well, any element of E is going to annihilate this thing here, because when I contract with one of them, but all of them are in the annihilator of E. So since they are in the annihilator of E, all of them will annihilate its volume form. And on the other hand, since I took the volume form of the annihilator of E, if I take any form in the annihilator of E and I do the wedge product with the volume form of the annihilator of E, that's 0 as well. Okay, so I recover this other example I had before. Okay, So the only thing with all these examples is that you can see that they do not satisfy, okay, they are not so good for us because they do not satisfy this thing. Here, this is not 0, okay, in all these examples. But it's still good to have them in mind, okay? What about the examples that we are interested in, okay, which are a bit more involved, but those are our target, okay? What about, say, a complex structure, okay? So what about this L that was T01M plus T star 10M? Will I be able to write it as an annihilator of some form? Well, actually, yes. This L, because this is just the linear algebraic case made geometric, okay, is the annihilator of some, this case, M0 form, okay? And here, okay, n, the dimension of my manifold has to be 2m, okay? And so this is what I have the m there. And also, with this, we have, this exists locally, okay? The M0 form. It's not necessarily a global form, but okay. When it exists globally or looking locally, I have L as an annihilator of some form. Okay, it's the same as this one here. 0, 1 vectors kill M0 forms, and 1, 0 forms kill the M0 because the M is the top among the holomorphic ones. Okay, so what about the other example that was even more interesting? What about Lx minus I omega x TCM? Okay, can I write this as an annihilator of something? And the answer is actually yes. And this one here is going to be the annihilator of this thing here, e to the I omega. What is e to the I omega? It's just exponential of numbers, and you just do wedge product instead of product. Okay, so what is exponential of numbers? You take 1, then you take your number, then you take your number square. Okay, like the power series. I mean, like this square, but this square is going to be minus because I have the I, so it's minus like this, okay, and here I will have then, so the third product now with an I omega 3, so this in here, that's e to the I omega. So what I'm saying is that actually these elements are exactly the annihilator of this thing here. And if you think a bit about it, it makes sense, okay? Because look, the x, when it acts, the first thing it does with the 1 is that it kills it, okay? Because 1 is constant, so that's 0. And when it acts here is I omega x. But I omega x is precisely what you get when you do minus I omega x with the 1, okay? So you'll always have this thing that x with this thing, with this one here will be cancelled with minus I omega x with the previous one, by the way it is that, okay? So you can express my L as a annihilator of this differential, of this differential form of mixed degree, okay? So now, in general, why did I say, here I said something that I haven't justified yet because I wanted to show some examples, okay? Why did I say it's even better to have this property? Remember that when I apply twice, I get this in here. So why did I say that? So look at this now. If I have some element in the annihilator of phi, which is like this, if I act again, okay? This will still be 0 because I'm acting on 0, okay? But, okay, I know it's 0, but on the left-hand side, I can develop it a bit more, and I can use this thing that actually the left-hand side, if I forget for a second it is 0, I would do this. And now I know this is 0. So whenever the element phi is not 0, then what I have is that x plus alpha equals 0 for any x plus alpha in the annihilator of phi. And this, again, we proved it yesterday. If all the vectors are null, that's because the space is isotropic. So the annihilator of any differential form in with this action is isotropic. Okay, so that's actually very nice, but as you can imagine, we are still a bit far from our purpose, because okay, it is isotropic, that's great, but with a second, Dirac structures were not only just isotropic, but I wanted to be maximal. So, so are they, these annihilators, are they maximal? Okay, and this is just the beginning, because actually I also need that L intersection L bar equals just 0. Do they satisfy that necessarily or not? And also I need integrability. Are they involutive? Well, we've seen actually this in general is not going to be the case, because I already showed you all of the examples before were maximally isotropic. Okay, it's very easy to find an example which is not maximally isotropic, but the ones I showed before, they didn't satisfy this condition to start with. Okay, so then we see it's not going to be the case, and what the thing we can do is actually to characterize a bit better what has to happen for those forms to give me what I want. Okay, so are they maximal? Okay, not always, not always. And now I'm going to do a very, very intuitive proof. Okay, since we know what maximally isotropic looks like, okay, I can describe also these phis that give me maximally isotropic. What maximally isotropic looks like. What do they look like? They look like L, E, epsilon. Okay, and this I'm going to put quotes here just to give you a feeling of how one proves this. Okay, so the thing is that this epsilon here, you can take it out as a complex B field. Okay, remember I talked about all these transformations that were preserving the bracket, the pairing, and also the projection they preserve. Okay, there were diffeomorphisms and B fields. I consider real B fields in that sense, but you can consider the complex versions as well. So this epsilon, you can take it out with a lot of care, okay, because you have to, okay, if it's defined on some E, you have to pull it back, blah, blah, but essentially you can take it out. And now you can use the fact, and this we've done it before, that LE0, I described it before. It was one of my examples for an annihilator of the volume 4 of the annihilator of E, okay? Here, it's true, I consider as a bundle of TCM, and actually I was too quick to say that didn't satisfy L intersection L bar is 0, but it actually depends on E, okay? If E is the complexification of a real subbundle, it won't satisfy, but there are cases where it does satisfy that L wedge L bar is 0. What I do now is I plug in this epsilon inside, and the way it acts, okay, is just by multiplying here this volume. Okay, what is this? What is this epsilon? This epsilon was, to start with, it was a 2 form. Okay, so actually this can be read, this just very, very intuitive proof. Okay, so this can be read as my spinor being the action of some 2 form, and this action is E B plus I omega wedge product. Okay, these are sum of all those products of the exponential, and I take the wedge product with the volume form of the annihilator of E. Okay, this is what's called a pure spinor. Why? Because what's behind the scene here, and I'm hiding it as much as I can, is the Clifford algebra and the spin group, and actually the differential forms. This exterior algebra is the spin representation. Okay, and these are actually the pure spinors. But today I can't say more about that. Examples of these, okay, you can see that all the ones we gave, one, the volume of annihilator of E, E to the I omega, those are examples of these pure spinors. Okay, so I know how they have to look like, and I know the ones I've considered so far, they look like that, and that's why I had maximal isotropic. Okay, now do they satisfy this condition L intersection L bar equals 0? Again, not always, but I can express when do they satisfy it. And for this, you have to introduce some pairing on the spinors. Okay, so we define for 2 differential forms in here. First of all, and the notation, let me just use the notation T for the reverse operation, which is just if you give me a form like this, alpha 1, alpha r, so if I do the T, that means I have alpha r, alpha 1. Okay, so for those 2 forms and with this notation, we can define a top valued pairing. Okay, what does it mean? This actually is more scary than what I'm going to say, which is just, look, you take 2 forms and you do the following. You just transpose one of them, which is this operation I gave you here. You take the wedge product with the second one, and then you just look at the top component. Okay, so if it is this top component will be some form, that the only thing is I'm only worried about whether this is 0 or not. So actually this condition L intersection L bar equals 0 for, let me put it for, wait a second, I'm going to delete this. Let me put it directly, annihilator of phi intersects the annihilator of phi here like this, 0. It turns out that this thing here is annihilator of phi bar, okay? And this thing will only happen when for this pairing phi bar, this is going to be different from 0, okay? So this is characterizing when my differential form is giving me as an annihilator satisfying that property. And now you can check that 1 doesn't satisfy this property. Okay, why? Because yeah, I won't get to any top thing. Okay, so this is 0. I don't go to any top. And actually, the same happens with a volume form. Okay, the same happens if I have a volume form. This, it's too much. Okay, On the contrary, the cases I'm interested in, which is having an M0 form here. If I take an M0 form and I do the pairing with its conjugate, okay, this by definition is okay. The phi M0 transpose wedge the phi, but okay, this is like a 0n. And the t is only changing the sign. So this is actually plus or minus a volume form. This is not 0, okay? So it works, that for this is not 0. And the same happens with e to the power of this ei omega. If I take the conjugate, which is e to the minus I omega, and you do this thing, okay, you can check, actually, the best would be just, you can do this case if you want for n equals 4. Okay, but here you have to take t as well. And you take here minus I omega plus squared. So this thing, this pairing is actually a multiple of omega n, which, because this is a symplectic form, is again non-zero. So this operation with the forms is detecting precisely when L intersects L bar as a 0 subspace, okay? And the last condition, I'm just going to state it, are the involutive. So the fact is that you will have that the sections of L, this will give you a section of L, this is involutive, when L is an annihilator of a form, if and only if the differential of that form, the exterior derivative, is the action of some element on that field, okay? Look at that, I'm not saying it has to be closed, which of course when it is closed, it happens because you just take V equals to 0. But here you have V Tm plus T star M complexified. Okay, again, examples. So you can check that the examples that they satisfy this, they are going to work nicely, because if you take the exterior derivative of this super differential form that has degrees in many components, you can see that this is just this I, the omega wedge E I omega. But precisely, again, there is a thread between this property and integrability. Precisely when this is omega is integrable, this is 0, okay? So this is going to be 0. So in particular, for the 0 vector, it is satisfied, okay? And the same happens with the volume, the M0 form of a complex structure is also going to be 0. We'll see later an example when it's not necessarily 0. Okay? So let's see what I have done today regarding generalized complex structures. So the summary is, so we have this concept that looks nice. Tomorrow I will say why it is interesting, apart from being beautiful, which is sometimes the first motivation. These J's operators are equivalent to these complex Dirac structures with this, and at least locally, okay, they are going to be given by these annihilators of forms. And here, okay, I have to put such some many conditions. Phi has to be pure. Phi has to satisfy this in here. That is not 0. And D has to be, okay? So there are quite a few conditions, but still, okay, still it's going to be more illustrative to work on this side, okay? And we'll be able to feel better the generalized complex structures. So now, because I want to leave you also today with some question, some simple question, tomorrow I will talk about this thing of being local, and now I'm going to say one good thing about working with. I'm going to finish with why working with these differential forms. So why work with this? Okay, because with this we can detect very easily some invariant, which is the type. Okay, so the type of some form here, which can be, by the way, locally defined. Okay, is so it's simpler to say than to write. It is just from all the components, you take the minimum that is not zero. Okay, so this is the type. Okay, it is a function. Okay, because this may change along your manifold. Okay, again, the two examples that are with us all the time now. What is the type of a symplectic extractor? So the type of a symplectic extractor is the type of this form here, but this is the type of 1 plus I omega. Okay, I don't care. I have the first non-zero component, so the type is 0. Okay, and actually what you can see is that type 0 gives you always that your phi is of this form. Okay, because actually, I mean, if you look here, the answer is actually here. This volume form, this is actually zeta 1 like this, well, okay, with the as I put it before. So actually, this is the type. What's going on there? It's very much related to the subspace E at each point. Okay, so when the type is 0, this R is 0, so I only have e to the b plus I omega. And when I only have e to the b plus I omega, in generalized geometry, the e to the b is actually a symmetry of, is a B field. So this is considered like a kind of a diffeomorphism, and this is like the structure I'm getting. So you would say it's any type 0 structure is a B field transform of a symplectic structure. Okay. And the other example we have is like the type of omega of some, well, phi m0, which has only m0 part. Okay, I'm saying it already. It's an m0 form. So the type of an m0 form is m. Okay, and actually type m, which is the maximum type you can have, is kind of similar, okay, to complex. Okay, it's not so direct with the B field, but today and tomorrow it will be just, say, a transformation of complex. Okay, so as a matter of fact, the type ranges from 0 to m. Okay, and are there things in the middle? Yeah, there are things in the middle. There are structures that are not just type 0, which are transformations of symplectic structures, or type m, which are transformations of complex structures. Actually, you could take a product of symplectic and complex. Okay, you take a product of symplectic and complex, so that this has type in the middle. Okay, what's the story about this? Okay, this is boring. Okay, what is interesting is the example I'm going to leave you with. So, and this is quite doable. I would say it's more doable than the question I left you yesterday. Okay, so consider C2 and consider coordinates z omega. Okay, and now consider the complex form here on this C2, which is z plus dz wedge d omega. Okay, so at each point, this I claim it is giving me a pure spinor. Okay, and actually it will be describing one of these generalized complex structure. And this is what I'm proposing to you, is that actually check all the properties here. Okay, check all the properties. By all the properties, I refer to, so the ones I wrote just a second ago, which is pure, that the pairing with its conjugate is non-zero, and that d of phi has to be, and now v cannot be zero, because if you see, if I take the exterior derivative of this, I get dz. I don't get zero. Okay? And the interesting thing about this, which is not boring at all, is that here the type is changing. Okay? Because this has only two components, 0 and 2, in a four-dimensional manifold, which is C2. Okay? But look at this. Z, the function z, along z equals 0. If I, okay, z equals 0, it has a type, actually type 2. And in the rest of C2, it has type 0. Okay, so this is a type changing structure. So this is how I wanted to finish my lecture today, with this example for you to check the properties, and also to explore, if you want, a bit of, okay, what kind of a structure is this? Okay, so you can give it a thought, and tomorrow we'll justify why generalized complex geometry is interesting. We'll see where this very simple example can take us, and then I will talk about this very recent work on complex Dirac structures. And that will be all. So thank you for your attention.
Thank you very much, Roberto. There's any question? I have a little question, but maybe you will answer this tomorrow. Is why to use, I have it here, generalized complex structure and not just Dirac complex structure?
Well, the thing is, as you see, generalized complex structures are a particular type of complex Dirac structures. Okay, they satisfy this extra condition. Okay? The thing with generalized geometry and Dirac geometry is that essentially, if you want, they are the same in the sense that they are working on this Tm plus T star m. Okay, my feeling is that Dirac geometry, when it started, it was more of a way to fit in these things, to have this a structure when I have constraints and symmetries. And generalized geometry took that, but it took it to the next level, which is I'm going to redo geometry by thinking about Tm plus T star m as a replacement of Tm. I'm talking only about generalized complex geometry, but you can talk about generalized metrics. You can talk about many structures by just replacing this Tm with Tm plus T star m, and also really believing that your diffeomorphisms are not just diffeomorphisms of your base manifold. They are actually also these B fields. Okay, so somehow in generalized geometry, you really extend this idea everywhere, and you do believe strongly that you have new diffeomorphisms. Okay, so it's more of a change of mindset. Okay.
Okay, thank you. Is any other question?
Hello. I was wondering. We saw that this is a cool setting to study both complex and symplectic structures together with a unified point of view. I was wondering what happens to the peculiar particular features of symplectic and complex geometry respectively, like for example Lagrangian subspace on one side, or totally real or totally imaginary subspace in the other side. There is another unifying point of view for this aspect.
Yeah, well, it really, I mean, I have to give you a very like open answer, okay? Because of course, generalized complex geometry is taken from these two worlds, the symplectic and the complex world, okay? So there are phenomena that are very different in one and the other. So, okay, sometimes you may get to some analog more towards the side of complex geometry, because, as you see, we've defined generalized complex structures as a complex operator. So in this sense, somehow they are very complex. But on the other side, they can be very symplectic, because by what I just said, generically, if you take like a random generalized complex structure, the chances that when you express it as an annihilator of a spinor of this differential form, the zero part doesn't vanish, this is probability 1, okay? So actually, generically, your generalized complex structures are symplectic, okay? So now for every concept, you can try to fit it in within generalized complex geometry, and the results may be very diverse, because some generalized theories is just, okay, you are doing generalized for the sake of doing it, but sometimes you really, you will be able to really find something new, and those are the paths you have to pursue. Let me put you an example, even though you didn't say it, is that of, for instance, what happens when you deform generalized complex structures, or what happens when you deform generalized complex structures. So you can deform them, and the deformation theory of generalized complex structures, so it resembles the deformation theory of complex structures, but it has some extra components. And actually, the funny thing was that those extra components were observed before and were expressed in a different language. So there were some deformations that somehow went away, like went off the space of complex structures, were deforming to somewhere else. And all of a sudden, you have these new deformations within this framework, and it all makes sense. Usual complex structures and those other deformations that were strange, they are all parts of the same thing. Okay, I'm aware it's a very open answer, saying, okay, so it very much depends on the case. Okay, so but for me the important thing is that you don't really have to give answers to every little detail of symplectic or complex. You just actually have to discard the ones that are not interesting and keep on with the ones that are interesting, because of two reasons: relation to previous theories, or because the theory itself is interesting. And this is what I will show tomorrow with more examples.
Any more questions? Okay, we can send Roberto again. And the third lesson will be tomorrow at 11, I think.
Okay, so see you tomorrow then.
Tomorrow.